All right, welcome. Today, we're going to build the ultimate performance toolkit for all you Delphi developers out there. If you've ever been frustrated by a sluggish UI or a process that just takes forever, you are in exactly the right place. We're going to make your applications fly. Let's get into it.
You know the feeling, right? That progress bar that just sits there. The UI that stutters every time you click. It's probably the #1 complaint users have, and it's a problem every single one of us has to solve. So, the big question is, how do we actually fix it?
So here's our game plan. We're going to start from the outside, looking at powerful external tools, and then work our way in to the core ideas behind your own code. And by the end, you'll have a complete mental toolkit to diagnose and destroy any performance bottleneck you run into.
Okay, first things first. We have to figure out what fast even means. It sounds super simple, but honestly, performance isn't just one thing. It's a totally different beast depending on what your application is actually trying to do.
You see, good performance could mean a user interface that's so smooth, the user never even thinks about waiting. Or it could be about a heavy-duty calculation, finishing in seconds instead of dragging on for minutes. And for a server, well, it might mean handling thousands of connections at once without even breaking a sweat. So the most important first step is always to define what fast really means for your goal.
Okay, so you found a real bottleneck. Sometimes, no matter how clever your Delphi code is, you just hit a wall. And when that happens, it's time to reach for the power tools in your toolkit. External libraries.
For those jobs that need just raw, close-to-the-metal speed, you really can't beat highly optimized C, C++, or even assembly. A perfect example of this is the FastMath library. It uses handcrafted assembly code to do vector and matrix math at lightning speed, giving you a kind of performance boost for certain tasks that Delphi just can't match on its own.
So C++ libraries are awesome. They're super powerful. But there's a catch. Your Delphi application can't just talk to a C++ library directly. Under the hood, they handle things like objects and memory so differently that they basically don't speak the same language.
So, how do we get around that communication barrier? Simple. We build a bridge. We create something called a proxy DLL. Think of it like a universal translator that you write in C++. It sits in the middle, taking all that complex C++ stuff and exposing it as simple functions that Delphi can easily understand and call safely.
And this workflow just lays it out perfectly. You've got the C++ library on one end, that C++ proxy in the middle doing all the translation work, and then, on your end, a nice clean wrapper class in your Delphi code. It makes using that powerful C++ code feel just as natural as using any other Delphi component. It's a really elegant solution.
Now, those external power tools are fantastic for those really tough bottlenecks. But true performance mastery, well, that comes from looking inward. It comes from understanding the structure and the logic of your own code. And this is where a little bit of theory goes a long, long way.
To really get a handle on our own code's performance, we need to talk about something called Big O notation. And look, don't let the name scare you. It's really just a simple way to talk about how much an algorithm slows down as you give it more and more data to work with. Does it stay fast, or does it grind to a halt?
Let's just break this down. An O1, or constant operation, is basically the holy grail. It takes the same amount of time whether you're dealing with 10 items or 10 million. O log n is also fantastic. It gets slower, but really, really gradually. And then you have ON, or linear, which just means if you double the data, you double the time. Understanding these basic curves is absolutely the key to writing faster code from the start.
That theory can feel a bit abstract, I know. So let's make it super concrete. We can apply this big O idea directly to the most basic hand tools we have as programmers, the data structures we use every single day.
So just take a simple list. If you don't bother sorting it, adding a new item is crazy fast. It's an O1 operation. You just tack it on the end. But finding something, you might have to look through every single item. But on the other hand, if you keep that list sorted, finding an item is blazing fast, an O log n operation. The catch? Now, every time you add something, you have to find the right spot for it, which makes adding things way slower. It's a classic performance trade-off. And this is where the dictionary, or T-dictionary in Delphi, comes in and basically saves the day. It uses a clever trick called hashing to instantly figure out where an item belongs. And what this gives you is the best of both worlds. You get near constant time, basically O of 1, for both adding things and finding them. It's an unbelievably powerful data structure for so many situations.
So,
We've looked at the external power tools, and we've sharpened our internal fundamental hand tools. Let's put it all together and see what our complete performance toolkit really looks like.
And here it is, the whole shebang. You've got your heavy-duty power tools for those extreme cases, linking to C++ libraries, using assembly for that last drop of speed, or even offloading huge jobs to the GPU with something like OpenCL. And then you have your everyday essentials, understanding complexity with Big O and making smart choices about your data structures from the get-go.
And that really brings us to the final question, the one that every great developer asks themselves. The next time your application starts to feel slow, what's your first move? Do you immediately reach for a big external power tool? Or do you first take a look inward and sharpen your own fundamentals? The answer to that question is often what separates good code from truly great code. Thanks for tuning in.